People sometimes ask me, what's C#'s best feature? And it's not a single feature that makes the language unusual. If you plot a graph with at one end you've got highly low-level performant languages, and on the other end you've got highly expressive languages, you know, like assembly language at one end and Lisp at the other. What makes C# unusual is it spans quite a big range in there. So it's got features that allow you to program in a low-level performant way and getting close down to the metal, and also it's got highly expressive features as well. So some of these low-level performant features, the ability to have your own value types in there, custom value types, so you can avoid overloading you can minimize the load on the memory management. But even better, you can bypass the memory manager altogether, right? With pointers, you can allocate your own memory. And you can also bypass the entire type system and all runtime checks. And you can also do a lock-free concurrency in C#. So, you know, if you're wondering, obviously the GC is pretty good nowadays and it's quite efficient, but there's times when you want to go that extra step and bypass it. You can do that in C#. But at the other end of the scale, at the expressive end, you've got these kind of features. So we've got things like asynchronous functions. So who uses asynchronous functions? So we've got, how many people are C# programmers here? So you've got about a third or quarter. So the rest of you, Java, you do programming in Java. So this is something that will probably come to Java soon, I imagine, because C# started out as a rip-off of Java, basically. But then eventually the Java folks said, look, the C# guys have added some pretty cool things. They started adding those features back to Java. So this is something that C# has, and it effectively abstracts away the difference between the present and the future. So you can program the future as though it were present. Lambda expressions closures, you have those, I believe, now in Java as well. Query comprehensions, and these allow functional programming patterns, which reduce and cut clutter and repetition. Now, expression trees, again, that's a feature which allows you to treat code as data. We'll look at that in a minute as to how that's useful. So I'm going to give an example now of where I've recently used all of these in one system. So some of you are familiar with a product which I've written called LINQPad. And it's if you're in the .NET world, you'll probably be familiar with it. And if not, then you can think of it as a scratch pad for .NET languages. So we can do things like put in an expression in here like 1 and 1, and we get 2. Or we can put something more complex like in there, like I can put type of int in there. And that's quite a complex object. It's a type object, and LINQPad lets you drill down into all these inside the properties and fields in there. So that's quite a sophisticated interaction between what you're running and the host process. But recently I added a feature to LINQPad where it includes an integrated debugger in there. So what you can do now is we can step through that. We can single step through that and watch how the variables change as you run that. Now, this was an interesting feature to write. Has anyone ever tried to write a debugger before? I can tell you the only thing harder than writing a debugger is debugging a debugger. Right? And one of the challenges, the first challenge I had was that in order to debug a process, you have to have the process you're debugging has to be different to your own process. So that means that every query now has to run in its own process. So I had to create a separate process container for every query, and that now has to communicate in a fairly rich way with the host process so that you can do that thing we saw before where we dumped out the type of int. So to make that work, I needed to come up with some kind of way of communicating between the processes. And I realized I had some quite stringent requirements. It had to be really fast, particularly regarding the latency had to be very low so that it doesn't slow down your program at all. And it needed to be asynchronous. So if because there's always a chance that you can write whatever you like here. You can write something which throws a Stack Overflow exception, right? And that crashes the process. Now, if it's in the middle of talking to the LINQPad host process, then that's not going to be very good because the result will never come back. Now, if that's a blocking call, that's going to block the LINQPad user interface and it will crash. So I wanted completely asynchronous, cancelable, and I wanted it to be very performant. And I realized that none of the built-in kind of libraries or solutions are going to work. So I thought, how about rolling my own from scratch? So we're going to start with the lowest level thing we can possibly do. The lowest level we can communicate between two processes is shared memory. We just allocate a block of memory, and we have both processes reading and writing to that memory. So that's the lowest level, and I want to be able to literally instantiate an object in another process and call methods on it. So is it possible to write something like that, and how do we do it? This is the challenge we've got. And this is the basic design that I came up with. It's fairly simple. So at the bottom level, we've got called a pipe, which is similar to a Windows pipe, but faster and completely asynchronous. So a pipe is just a mechanism for sending byte arrays from one process to the other. Real simple. You have a send method at one end and a receive on the other. So I wanted to create a pipe with an input and output pipe. And on the top level, I wanted a channel, which is a high-level construct that gives you proxies. So that lets you instantiate objects in another process and then call methods on them or properties on them. So the requirements for the low level, let's look at the pipes requirements. We want to send byte arrays to another process. We want it to be very low latency, asynchronous. And my first thought is it needs to be bidirectional. But then I thought, that's going to complicate it a lot. We don't need that. All we need to do is create two pipes, one each way, and now it's bidirectional. So it can be unidirectional. So now, I'll show you how the shared memory works in a basic way. So this is the API. .NET provides a wrapper, an API, to let you get at shared memory. So this is how you create 1,000 bytes of shared memory. That name identifies it. So if you do the same thing on another process and you have the same name, you can talk to each other. You get the same block of memory, right? And this is a way of accessing that shared memory. And this writes at the offset 500, it writes the integer 123. So I'm going to do that right now. And then in another process, I'm going to read that. Let's do it here. So we're going to open existing with the same name. And now I'm going to read the integer at offset 500. And we should get the same result back, which is great. Now, the only problem with using these methods like readInt32 is they're kind of slow. Like if you're doing a lot of them, it's not great. So you can do something else. We can use pointers, right? This is something that basically C# stole from C, right? It's the ability to directly reach into the memory and just do what you like to it. Right, so this is how you get the pointer. You call this dangerous get handle, right? They don't want you to use pointers. You only use them if you really need them for performance. Then they're really good. And this is pointer arithmetic. We're moving ahead 500 bytes. We're now casting it to an int pointer so that now we can store 123 integer, which is 123000 in bytes. It's 4 bytes. So that will give us the same result, but that's faster now. So assuming now we're able to read and write memory, let's see what sort of protocol do we need to create a pipe, which is a mechanism. We want to be able to send byte arrays to another process. So here's how we can do it. We're going to start out with a block of shared memory like this, and we're going to reserve the first 5 bytes as a header. So the ones in blue and yellow. Now, I want to write a message of 3 bytes, 1, 2, and 3. So first thing I do is I length prefix it. I write the number 3 to memory, and then I write the 3 bytes. Then I increment the header in blue to 1 so that it shows that we've written a message, and then we flash that inter-process signal at the bottom that tells, so the other process that's reading the pipe is waiting on that signal. When that activates, it then looks and sees that the header is now 1, which is greater than 0, which it would have had before. And so now it can read that message of 3 bytes long. And then when it's finished reading it, it goes back and reads the header again. And says, is that now 2? No, it's still 1, no more messages. And then it goes back and reads it again. And it spins for about 1,000 times, right? So that, and then if it, after 1,000 times it's still 1, it will then wait again on that inter-process signal. Now, the reason for spinning 1,000 times, it means that if there's a lot of messages going really quickly, then you don't get the overhead of having to wait on that interprocess signal, right, which is relatively expensive. So then we want to write another message, this time 5 bytes. So we'll write the 5, the prefix, length prefix, we'll put the 5 bytes, and we'll increment that now to 2. The other will flash the interprocess signal, and this process will repeat. The other one can read it. And eventually, we're going to fill up that block. So what do we do when we've filled up the memory? We want to write another message. There's not enough room for it. Well, the thing I'm doing is very simple. We just create a new block. We create a new one, and we start all over again. Right? So we just keep creating new blocks. And we keep those old blocks in a list somewhere. And every now and then, we're going to need to clean that list up. So how we do that is that the reader, when it's finished reading it, it sets that yellow byte in the header to 1. Right? So the writing process writes 4 zeros to indicate now that's finished. It's going to write into a new one. The reader now sets the yellow byte to 1. And then at some point in the future, then memory can be disposed. Now, there's some really important characteristic to the way we've done this, which is there are no locks. Normally, you've got 2 processes or threads reading, writing same memory. You need locks or things go horribly wrong. We've managed to do this in a way that's completely lock-free. And this is important because this gives us a big performance gain, because the sort of lock we would need to make this work is not an ordinary lock. It would be an inter-process lock. They are way, way, way more expensive and slower than ordinary locks. And they would cause other problems too, in that, let's say, the debugger kicks in and breaks. Now, when a debugger hits a breakpoint, all of the threads freeze on that process. Imagine if it held a lock, an inter-process lock at that point. It's going to freeze the other process. It won't be able to access the pipe. So we've managed to do it in a way that's completely lock-free, which is quite cool. So we're going to implement this now in LINQPad. So here's the pipe and what it looks like. So I won't go into all the details of the code too much in here. I've created a base class called safe memory mapped file. That gives us the pointer. I've got a mechanism here to try and minimize the chance of dangling pointers. That's basically what that is. A dangling pointer is when you've got a pointer that points to memory that's now been disposed, right? And then horrible things happen. So we need some care there. That's our pipe. That's the abstract base class for a pipe. We create the shared memory over here. And that's where we write the data in there. And the particular part I want to focus on is on the input pipe. This is where we set the thing up. Let me show you the constructor. So the constructor, we give it the name, and we give it an action of bytes. So this tells it what to do when we get a message. It's kind of like an event in C#, or in Java, I imagine there's something similar to an action of bytes. So it's a delegate. It says, this is what you're going to do when you get a byte array. Run this bit of code. You put some code in there. You could also do that with an iObservable of byte array. And this is a loop where we look for new messages, right? So that's the spin cycles, so that we spin 1,000 times when we get a new message. When the spin cycles go to 0, we wait on the new message signal. There's something in here which I want to point out, which is quite important when you're doing lock-free code. And there's a couple of places in here we've got a memory barrier. Now, when you're not using locks, you run into a problem in that the underlying processors, the Intel and AMD processors, they make a guarantee which kind of breaks down when you start doing multi-threaded code or you have multiple processors. So it basically the processors reserve the right to reorder your instructions, your reads and writes. But they guarantee that those reorders will not change the outcome as long as it's a single-threaded program or a multi-threaded program that uses locks. Now, if those don't hold, then now those bets are off. So it can do some pretty nasty things in terms of reordering reads. So now you need to look at the underlying memory model, and in this case, we need to insert 2 memory barriers. And what this does is a memory barrier prevents any reordering occurring across that barrier. So the time when we're vulnerable is right over here, in the time when we're reading, in between reading the data and reading the header, when we're doing that spin. That's when if those instructions got reordered, that could cause it to fail. So we've got two memory barriers in there to prevent that happening. So let's run that now and see what we get. So the first thing we'll do, get that pipe back to the pipe, run the demo. The demo is quite simple. It just writes a message of 3 bytes and then a message of 5 bytes in there. So when we run that, we should just see that message getting dumped out. And I'll run that and we'll get a 3 and a 5 byte message. So that works. And now I'm going to run this stress test, which will give you an idea of the performance we're going to get with this. And we're getting around, this is on a laptop, we're getting about 800,000 messages per second in there. That's pretty low overhead, around a microsecond a message. Now, I have got all of the code on this. Is all available for download. So from LINQPad, you go to the Samples tab and hit Download, Import More Samples, and scroll to the bottom. You can download all these and use them and do what you like with them if you want to use them yourself. So that's pretty much, that summarizes the low-level bits. So now we're using the pointers and low-level stuff to get the performance and interoperability we need to make that work. So the next stage is in that higher level. So here we're going to now go to back to the model. So now we need to write the channel and proxy. So what we're trying to do now is we can communicate, we can send bytes from one process to another, but we now want to instantiate objects in another process and call methods on them. That's going to be a bit harder. So the feature that we're going to be, these are the kind of features we need. Client activation means that we instantiate objects on another process. We want to pass in parameters and get a return value back. So we need to have some way of serializing those values and getting them back. Propagating exceptions that's quite easy. Exceptions just a return value really that you throw. It needs to be asynchronous. Marshalling and unmarshalling means that we can send the proxies themselves can be serialized across the wire. That's really useful. I won't go into that in this session, but that's all in the code, how that can be done. And we need to be able to write it in less than a week. And that means we need to get most of it basically working in a day. Because with most bits of code, you spend one day kind of getting it mostly working, and the next 4 days debugging it and getting that last 10%. So the way it usually works, right? So what we'll do is I'm going to start with the most interesting challenge in doing this, which is we need a way of, if I want to call a method, foo on a class called bar, I need a way of describing the method that I want to call and the parameters that I want to send across. So how we can do this is using a feature called expression trees in C#. And how this works, let's start with something really simple. This in C# is a delegate. Action is a delegate. It describes a parameterless method. So when I call that method foo, that takes a parameterless method in. I can pass in a lambda expression. This is a bit of code and says, write out hello world. So when I run this, it's going to execute that and write out hello world. Now, to anyone that's done functional programming, this will seem so trivially, simple. I wonder why am I even bother demoing it. But this is essentially how you treat a function as a value in C#. So, but what we can do in C# is go a stage further and change that action to an expression of action. What this does, it tells the compiler that we want to treat this code as data. We want the compiler to construct a code DOM, an abstract syntax tree that describes the code that we pass in. So now, if I dump out that variable, I'm going to see a description of calling console.writeline hello world. So have a look at that. And now we can see in there, we've got a lambda expression, and in there the body is a method call expression. The method is console.writeline, and these are the arguments we passed in of type string, constant, hello world. So this is how we can describe the method that we want to call in the other process. So these expression trees are critical to making this work well, because any other way is going to involve a lot of compromises. With this, we get complete static type safety. So we can rename anything, and it renames it everywhere, into call sites as well as the callers. So let's have a look at, flesh out what the, I've got another example here which shows in a bit more detail how we can look at that. So if the body is a method call expression, let's dump out the method and the arguments. So we made that more explicit here. So now we've got the method is the write line, and these are the arguments. So let's flesh out something basic in terms of what this remoting framework is going to look like. So we'll create something called fast channel that encapsulates what we're going to do. And this is how we new up an object. So if I want to instantiate a new instance of remote class, I do that, and that returns a proxy of remote class. That now lets us call methods on the remote class. And then I want to execute a method called SumRemoteMethod. I do it by passing in a lambda expression, and now these are the arguments that I'm going to pass in there. So this is what the fast channel will look like. It will have an input and an output pipe. It needs to be bidirectional because we need to get return values back and exceptions back the other way. This is how we new up something. We instantiate it. We have a method activate of tremote. We create that proxy, and then we will send something across the wire, right, across that pipe that tells it to instantiate the object. This is the demo remote class. I want to activate a method like that. Call a method SumRemoteMethod. That's the proxy here. This is what the proxy will look like. That's our run method. It's an expression of action of tremote. So it operates on the tremote class, and the expression means we want to treat this code as data. So then we're saying we're only going to allow simple method calls. So if the no type is not an expression call, then we're going to throw an exception. I'm going to dump these out for now. But this is what we'll do in real life. We'd serialize that method call and send it down the wire. Now, before we get any further, we'd also need a method that returns a value, right? So this is a void method. If I call this for a void method, but if I want to call it with a method that returns something, I need an eval, which returns a T result in there. So it's getting a bit more complex now. The signature, so the expression again, treat this code as data. This is, I want a function that takes in a tremote and returns a T result in there. Now the final thing is, remember I said one of the requirements is that everything must be asynchronous in here. And this is a really important requirement because we can never be sure that we're going to get a result back. Right? The debugger might have kicked in and stopped all the threads, or you might have crashed. So I don't want any method to be blocking. So everything is going to return a result in the future, not the present. Now in C#, to do that, you wrap it in task of tResult. That's how we do futures in C#. And that allows us to use the await syntax. So here's now what the eval will actually look like. So again, treat this as code as data. We want a function that takes in the remote type and returns a T result in the future. That's a signature. So that's the power of the language when you're using it at the most expressive end. We can describe an awful lot just with that signature. It's fairly abstract stuff. So I'm going to run that now. I'm going to implement the whole thing. This is the whole fast channel. This is a few more pages of code. And I've got a method with some things that we want to call here, like an add method and a get process ID method. And I've got an asynchronous one there. This also lets you call asynchronous methods as well as synchronous ones. And this is an example of how we're going to use it. So I'm going to instantiate an object called foo. We're going to get the process ID, a simple property get. And then I'm going to add two numbers together. I'm calling that method called add. And then I'm calling the asynchronous version of that. Now what's interesting here is all of these are returning values in the future. But it looks like that the simple synchronous code, because we're using this await keyword. And this is critical to making this tractable. If it weren't for this await, the whole thing would be way too messy with continuations everywhere and callbacks. So this is a really good feature that allows us to do this. So we can write code that looks like synchronous code, but it's fully asynchronous. And so when I run that, this all works perfectly and gives us the results we're expecting. But having demoed all of that, it does kind of look a bit smoke and mirrors, doesn't it? Because it's all in LINQPad, and I wrote LINQPad, so I could have cheated and put a backdoor in there to make all this demo work. So I'm going to do something now to make this a bit more graphic. So I've written something in Visual Studio, which is a simple Windows Forms application. Got a simple form there, and I've copied and pasted the fast channel code in there, which I've written. That's all copied and pasted in there. And then I've written a class called remote control. This is the one that we're going to instantiate remotely from LINQPad. I'm going to tell it, instantiate this, And I've got a single method for now called setColor, and that sets the background color of the form. So we're going to run that now. Go back to LINQPad. That's our main form on the right, LINQPad on the left. And I'm going to run a method on there. Here we are. So I'm going to create the channel. I'm going to activate the remote control, new it up, and then I'm going to call a method on it. And that method will be p.setColor to red. So that's going to now set the color to red. Let's run that, and it sets the color to red. So we really are doing it remotely. Now I'm going to make this a little more elaborate. So we're going to go to the next one. And I'm going to cycle through 10 different random colors. So I'm calling getRandomColor, and we're going to then wait for a second and run this again. So now it's going to cycle through 10 random colors. So we really are controlling this thing remotely. And the final thing I want to do is, I've also got a method in there. Go back to the demo. I've also got a method which lets us display an image in the on that form. So that method is called showImage. It calls showImage on there. And that means I can send a whole image across the wire. And we're going to do that. So the image I'm going to send is a Mandelbrot fractal. So to do that, I've written some code to render and draw Mandelbrots. So this class handles all of the code to draw Mandelbrot fractal, and it does it using parallel loops, right, in the parallel library framework. So this does that the parallel loops gives us back an image containing a Mandelbrot fractal. So what we're going to do now is we're going to await the draw Mandelbrot fractal. That gives us a frame, and then there's the code to do the draw Mandelbrot. So we ask it for the window size on the other side, and then we create a frame with that size. We get the image from our calculator, and then we're calling showImage. So we're doing all the computations in LINQPad, and we're using this other process to do the rendering. So let's run this now and see what happens. And there's a Mandelbrot fractal on the other side. The other thing I've done is I've created another channel which lets that talk back to LINQPad, so that when I click on this, it's going to call back into the LINQPad code, and it will enter this bit of code here. So when I hit the click on here, breakpoint, there we are. It's going to now run this code here. And what I'm going to do is I'm going to zoom in and re-render the Mandelbrot where I've clicked it. So we'll get that off, the breakpoint off, and continue running. So now we can zoom in onto the Mandelbrot fractal. So all of the computations are occurring in LINQPad, and all of the graphics rendering is occurring in a separate process in there. And so we're getting pretty good performance with that, and pretty good latency. Eventually we'll get repetitions of the Mandelbrot set. So yeah, I mean, to summarize, I mean, whatever language you're using, it's going to have some really good features that distinguish it from other languages. So if you want to really be getting the most out of it, you ask yourself, you know, what's the best feature of the language you're using, and are you using and making full use of it? And if you're using C# or you're thinking of using it, then the breadth is the best feature, the ability to do both really high-level stuff and low-level stuff without having to drop to another language. So any questions on that?